Hi everyone. Today I'm going to discuss series of matrix structural analysis examples, in particular about beam problems. So there are a lot, or there are many examples on beams solved by matrix structural analysis approach, or matrix approach, and I hope that all the problem types on beams will be covered in my examples. So for the first part, there are three or four examples, and I I divided the series of examples into three slides so that it will be uh, reduced to at least 1 hour long video. And if it is your first time to see my YouTube channel, please don't forget to subscribe so that I will be inspired to do many videos regarding civil engineering subjects. And I hope that you will enjoy in your journey and you will learn a lot from my videos. So enjoy watching. So let's now have series of examples on beams. So for the first problem, for the fixed-ended beam shown, E is 200 gigapascals and I is 150 times 10 to the 6 mm to the fourth. So determine the nodal displacements and member forces. So let's determine the displacement at C. Only C has displacement. So this is 2 by 2. There are only 2 degrees of freedom because at A and B they are fixed. So first, divide the span into two parts, EC and CB. So take note, this is A, node 1, node 2 is C, then node 3 is B. Fixed moment formula, imagine that C is fixed, remember? So our fixed formula is 45 times 3 square over 20, W L square over 20, where L is 3, and it is 20.25 counterclockwise. Remember the effect of fixed moment, or the fixed moment's sense clock. It should be counterclockwise at the left and clockwise at the right. So fixed moment CA is 45 times 3 square over 30, so 13.5 kilonewton meters, so it is clockwise here, CA. Then for CB, there is no load in CB, so fixed forces will be 0. Next, let's solve for the fixed reaction or forces by taking moment at one end. So call that FA, then that's F sub C. So summation moment at 2 equals 0. So we have FA times 3 plus 13.5 equals 20.25 plus 1 half of 3 times 45 times 2, the moment of the load. So FA times 3 plus 13.5 equals 20.25 plus 1 half of 3 times 45, then moment arm is 2. Solving for FA is 47.25 kilonewtons. Then for F sub C, summation forces Y equals 0. So for F sub C plus 47.25 equals 1 half of 3 times 45. And we'll get F sub C equals 20.25 kilonewtons. So the nodal forces would now be at node C or at node 2 would have a downward force because these are fixed forces. So the nodal force we have downward opposite to F sub C 20.25, and because this moment is clockwise, so we have a counterclockwise moment of 13.5. So it's positive and this is negative 20.25. So let's now set up the equation. Remember our guide for the stiffness matrix of a beam. 12 EI over L cubed, 6 EI over L squared, 6 EI over L squared, 4 EI over L. Then we have here negative 12 EI over L cubed, 6 EI over L squared. Then the negatives of this, the negative of the first, then half of 4 EI over L is 2 I over L. Then the third row would be the negative of the first rows. So negative of the first rows. Then the fourth row will be copy the second row and interchange column 2 and column 4 position. So you look at column row 3. Row 3 elements would be the negatives of row 1 elements. And row 4 elements, we just copy. Then don't forget to interchange 2 EI over L here, 4 EI over L here. So that's the technique in memorizing the global stiffness matrix for a beam or member stiffness matrix. Then we have member 1, which is member AC of the forces and its case or this force coefficients. So because EI is constant, we just treat EI is 1. So 12 divided by 3 cube. So KEC is 12 over 3 cube. So these are the values. So 12 over 3 cube is 4 over 9. 6 over 3 square is 2/3. Then the negative of 4 over 9 here. Then copy 2/3. Remember? Then this is also 2/3. Then this is 4 EI, 4 times 1 over 3, so 4/3. Then this is the negative of this value here. Then this is 1/2 of 4/3, so 2/3. Then we copy the first row, then change the sign, remember? Then we copy the second row and the second row in the fourth row, but don't forget to interchange position between 2/3 and 4/3 here. So that's the technique. Then for member CB, we have 12 over 2 cube is 1.5 or 3 halves. Then 6 over 2 square is also 1.5. Then the negative of the first, copy the second column element. Then this is 6 EI over L square also, so 1.5. This is 4 over L, so 4 divided by 2 is 2. The negative of 1.5 here, and this is half of 2. Then copy the negatives of row 1, then copy row 2, but don't forget to interchange position between 1 and 2. So that's it. Then because this is designated, the displacements at C is designated as 3 and 4, U3 and 4, so we are only interested of expanding 3 and 4. So we have here the general, supposedly. This is 1, 2, there are 3 nodes, so times 2, so 6. The matrix is 6 by 6. The overall stiffness matrix is 6 by 6, or the global stiffness matrix for the beam is 6 by 6. But we eliminate rows and columns associated with zero displacements, which are rows 1, 2, 5, and 6, because there's no vertical displacement and rotation at the supports. Then it reduces to 2 by 2. So we delete rows and columns associated with zero displacement. So it is reduced to this matrix here. Negative 20.25, 13.5 as force matrix. This is the 2 by 2 matrix, then unknowns, U3 and U4. So U3, U4 equals the inverse of 35 over 18, 5 over 6, 5 over 6, and 10/3 raised to the negative 1. Then times the force matrix, negative 20.25 and 13.5. So solving for U3, U4, which corresponds to delta C and theta C, the vertical displacement at C, delta C, and the rotation theta C. So these are the values over EI. Then substitute the value of EI, which is for displacement, you divide, this is E times I is 30,000 kilonewton meter square. The technique in computing the displacement automatic in nm unit would be you just divide this by 30, which is 30,000 kilonewton meter square. So you just divide this by 30. But the slope, you divide this by 30,000 as a whole. So that's why if you divide negative 13.608 by 30, it is negative 0.4536 mm. And if you divide this 7.452 by 30,000, it is 2.484 times 10 to the negative 4 radians. By the way, how are these elements obtained? Of course, you have to fill up or fill in only the upper right triangular matrix or upper triangular matrix and take note of symmetry. So for example, 1, 1. So 1, 1 is 4 over 9. So you have there 4 over 9. This is 2. This is row 1, column 2 is row 1, column 2, 2/3. That's it. Then row 1, column 3 is negative 4 over 9. Row 1, column 4 is 2/3. Then 1, row 1, column 5, there's no common 1, 5 cell and 1, 6 cell. That's why they are all zeros. So they are also equal to these columns here. Then for 2, 2, we have 4/3 here, 2, 2. So that's why it's 4/3 also there. This is row 2, column 3. Row 2, column 3, there's only one, so negative 2/3. This is row 2, column 4, that's positive 4/3. Positive 2/3 rather, row 2, column 4. Then 2, 5, there's none, there's no common, and 2, 6, none, so 0, 0. So that's why here in column 2 we have also negative 2/3, 2/3, 0, 0. Then 3, 3. 3, 3, it's common to two cells here. There are two cells, so one is 4 over 9 plus the other one is 1.5. So 4 over 9 plus 1.5 is 35 over 18. Then this is 3, 4. 3, 4 is also common. There are two cells. 3, 4 is negative 2/3 plus 1.5. Negative 2/3 plus 1.5 is 5 over 6. So that's why this is also 5 over 6 by symmetry. Then this is 3, 5. 3, 5, there's only one cell. 3, 5 is negative 1.5. And 3, 6 is 3, 6 is also 1.5. So that's why in this column, we have negative 1.5 also and 1.5. Next, this is 4, 4. 4, 4 is common to 2. So 4/3 and 2. 4/3 plus 2 is equal to 10/3. So that's why it's 10/3 there. This is 4, 5. 4 and 5. So 4, 5, negative 1.5. So that's why 5, 4 is also negative 1.5. Then this is 4, 6. 4, 6 is 1. So that's 1. That's why 6, 4 is also 1. Then this is 5, 5. 5, 5 is common only to 1. And it is equal to 1.5. So 5, 5 is 1.5. Then this is 6, 5. Sorry, row 5, column 6. Row 5, column 6 is negative 1.5. That's why row 6, column 5 is also negative 1.5. Finally, 6, 6 is 2. Sorry, it's 2 there. Now, sometimes you need to have a technique that when you know that other rows and columns will have associated zero displacements, then you don't need to fill them up. Only the important cells must be filled up. Like, for instance, if you know that only U3 and U4 will have displacements, then you only fill up 3 and 4 cells here. Then you may not fill in this other displacement, other force coefficients or these cells here. They are not important in our solution. Okay, so this is are now the displacements at C. So I hope you know already the technique. If you need to change the units to mm, then just divide the value by 30 by EI, which is in this case 30,000 kilonewton meter square. But the technique is you just divide the it by 30. But for the slope, you divide it by the entire value, which is 30,000. Then the member forces. So for first member AC, this is AC. The elements would be supposedly P1, P2, P3, P4. But specifically, this member forces are P1 is actually the shear at A or the reaction at A. Then P2 is the actually the moment at A. P3 is the shear at C just to the left, and P4 is the moment C to A. So that's the meaning of P1, P2, P3, P4. You replace F1, F2, F3, F4 because this is for global and this is for individual member forces. So shear moment for that uh, element. Then this 1, 2, 3, 4, 1, 2, 3, 4. These are the force coefficients for member AC or member 1. All you have to do is copy all this and transfer it here. Then the displacement. So at 1, there's no displacement. There's no vertical or upward or downward displacement at A. There's no rotation at A. That's the meaning of this U2 here. And this one is the displacement at C, vertical displacement at C, which we already computed, negative 13.608 over EI. But because these coefficients have also EI, we don't care the EI because it will just cancel out. Then this is U4, 7.452 over EI supposedly, but as I said, EI will cancel out because this force coefficients of EI originally. Then, because only rows 3 and 4 will have displacements, then we may cover columns 1 and 2. They are not important. So to compute the final member force or final member forces, including moment, that's the general term for member forces. By the way, the fixed end forces are for FA, it is 47.25. It's here. Then MA or moment 1, this is the fixed end force, which is counterclockwise, and counterclockwise is positive, so that's why it's positive there. Then uh, FC left, FC left or F sub C, which is 20.25. That's the fixed end force for member AC. These are the fixed end forces for member AC. So 20.25, and for moment C to A, that's the meaning of this. Moment C to A, it is 13.5 clockwise, and clockwise moment is negative. That's why it's negative here. So to solve this reaction or shear at A, it is equal to, because the first two when distributed will be multiplied to the zero displacement. So we begin with negative 4 over 9 times negative 13.608 plus quantity 2/3 times 7.452, then plus 47.25, then we will get 58.266 kilonewtons. For the second row, moment A, negative 2/3 times negative 13.608 plus 2/3 times 7.452, then plus 20.25, we'll get 34.29 kilonewtons. For row 3, 4 over 9 times negative 13.608 plus quantity negative 2/3 times 7.452 plus 20.25 fixed and force equals 9.234 kilonewtons. Then finally, negative 2/3 times negative 13.608 plus 4/3 times 7.452 plus negative 13.5, you will get 5.508 kilonewton meter. Then for member CB, we have to copy this force coefficients for member KC from its stiffness matrix. Then the displacement, this is U3, which is already computed, negative 13.608, U4, 7.452, U5 is the displacement at B, which is 0, U6 is the rotation at B, which is also 0. So that's why we have 0, 0 here. So this time, the first two columns are important, and you may cover columns 5 and 6 because they are multiplied to corresponding zero displacement. So we only distribute the first two columns. 1.5 times the, by the way, fixed forces, because there's no load in member CB, then fixed forces will not be generated. So everything here will be 0. So that's why 1.5 times negative 13.608 plus 1.5 times 7.452, the rest is 0. Then plus 0 equals negative 9.234 kilonewtons. So note that we expect that the shear at C would be the same just to the left and just to the right. So that's why we have the same value here, 9.234, and although the second one is negative 9.234. Then for MCB, 1.5 times negative 13.608 plus 2 times 7.452 plus 0 equals negative 5.508 kilonewton meter. Then for shear B left, or this is automatic, the reaction at B. So we have negative 1.5 times negative 13.608 plus negative 1.5 times 7.452 plus 0 equals 9.234 kilonewtons. So take note that there's no change in shear between C and B. That's why we expect same shear. They are only opposite in signs. Then finally, for moment BC, 1.5 times negative 13.608 plus 1 times 7.452 plus 0 equals negative 12.96. So these are the member forces. For the reactions, so remember that positive moment forces, moment means counterclockwise at the left, or counterclockwise moment. So moment at A is negative 34.29. It is negative 34.29, which is opposite to this because remember, positive moment will have a bending which is smiley. And for positive bending, it means that at the left, the moment should be clockwise, and at the right should be counterclockwise. So this is moment at the left. Since this is positive, it is counterclockwise. But the positive moment is expected to be clockwise at the left. Remember? So clockwise at the left and then counterclockwise at the right end. And because this is counterclockwise, and we expect for positive moment clockwise at the left end, that's why the moment at A is negative 34.29 kilonewtons. And RA is 58.266, so it's just equal to shear at A. Then moment at B is negative 12.96 kilonewton meter, because this is negative 12.96 means clockwise. So at B, it is clockwise. Why is it negative? Because we expect counterclockwise positive at B for positive bending. Again, for positive bending, clockwise at the left, then counterclockwise at the right. But because we are given a value MBC which is negative 12.96, so it means clockwise at the right or at B. And clockwise moment at B means negative because it should be counterclockwise to be positive. So that's why moment at B is negative 12.96 kilonewtons. And RB, is simply equal to shear at B just to the left, which is 9.234 kilonewtons. That's it.